Okay, well, thanks very much to the organizers for the invitation to speak. This is the sequel to Matt's talk this morning. I'll try and make it as independent as I can. First of all, perhaps I'll remind you of what the theorem we're trying to prove is. I'll try and stick it over here so when I explain the conditions and so on, I can come back to it. So we have X is a GU n-1, 1 Shimura variety. Of some neat level. And in particular, there was no assumption about the ramification of the level at P or anything like that. M, a maximal ideal of a Hecker algebra T, or the Hecker algebra if you like. And well, the kind of ultimate goal of what one would like to prove would be that kind of HI of X with FP coefficients bar coefficients, maybe FP coefficients localized at M is 0 outside of middle degree. And that's not what we prove, but maybe that's what the kind of conjecture would be if M was sufficiently generic. Middle degree is, I guess, n-1 if M is sufficiently generic. And so we prove some cases of this. So the theorem is, let's see if I actually fit it over here. So theorem, this is going to be true if maybe the following things hold. There kind of exists a Gauss representation associated to M in the usual way. So representation rho M from, so I should have said that there's some auxiliary quadratic field E over which this unitary variety is being defined. So there's an n-dimensional representation associated to M which is irreducible. We want to assume that P is greater than n choose 2 plus 1. And assumption that this Gauss representation at P is, I guess, I can say n-1 on 2 regular. And I'm going to kind of merge the conditions into one to make it slightly weaker, but I'll say that the semi-simplification of this is not a sum of characters. So again, this is a condition I will explain. And then one more assumption, which was this assumption about the image. So the image contained SLN of K, it's contained in rho M, GE, contained in FP bar star, SLN of K for some, some finite extension. And then of course, I've slightly run out of room for the actual statement, but then these all vanish up to degree n over 2. N minus 1 over 2. Sorry? Yes, this. Yes, OK, you're right. So at the end, I could have written if this. Yes, thank you. OK, So I think as Matt stated, it was slightly stronger because we had a condition of R regularity and proved vanishing up to R as long as R was at most n minus 1 on 2. And in fact, you only need this condition here in degree n minus 1 on 2. But just for trying to fit this onto a board, I've slightly simplified things. And also, as Matt remarked, we could have made a different hypothesis here. We could have assumed something about the image being an induction from a character. And again, I'll come back to that. OK, so that's the result we want to talk about. And Matt kind of explained part of the argument, and an argument to explain how we were going to have some access to P-adic Hodge theory in this setting, how we could make any kind of study of this thing from using P-adic Hodge theoretic tools. And maybe I'm going to try and explain how, given that, how we actually then proceed. So there's this theorem of a kind of conjecture of Serre from, I guess, about 1972, which is then a theorem of Xavier Caruso from, I don't know, 4 or 5 years ago, which says the following. Let me make sure I state this correctly. So let's take k over qp finite. And x proper and semi-stable over k. And then we consider the cohomology of x over k bar with fp coefficients. Consider its dual, and maybe semi-simplify just to make the definition easier. And then it says that this has all inertial weights in some bounded range. I'll explain what that means in a moment. So contained in the range 0 up to I times ek, where ek is the absolute ramification index of this field k. So what does this mean? Well, this representation here, this semi-simplification is as a representation of inertia. So as a representation of ik, we can write this as a sum of characters, a sum of powers of fundamental characters. So you can write it, if we take the fundamental character of niveau n, you could write this as kind of omega n to the a1 plus pa2 plus pn minus 1, an minus 1, where the ai are between 0 and p minus 1. And these AIs are the inertial weights. This is the definition of the inertial weights. So for example, this says that if I take h1 of some semi-stable proper variety, and I look at its representation on inertia and look at all the characters that can occur, the only powers of the cyclotomic character mod p that could occur would be kind of 0 up to ek. In fact, sorry, I should just say 0 and 1. If I'm talking about the cyclotomic character being the first one, I'm assuming I'm unramified. So if I'm unramified, I can just get the cyclotomic character or the trivial character in terms of niveau 1 characters, but I can't get the cyclotomic character squared occurring in an h1. That's the kind of thing it says. So the way you prove this is, well, Matt kind of maybe slightly alluded to this. So Caruso proved some mod p comparison theorem, which showed that if I made the assumption that this quantity here was that most p was in fact strictly less than p minus 1. So not just the ramification index was less than p minus 1, but in fact the ramification index is less than p minus 1 divided by the degree of the cohomology. Then he was able to prove some comparison theorem for this object that allowed him to rate it to these linear algebra objects, these Broglie modules. And then essentially a kind of formal calculation tells you that these are the only characters that could possibly occur. And the reason there's no restriction up here about this being less than p minus 1 is, of course, if this is as big as p minus 1, then there's no statement at all here. These numbers are just defined to between 0 and p minus 1. And as soon as this quantity is bigger than p minus 1, this statement is kind of vacuous. Okay. So the idea of what we want to do is to kind of have some generalization of this statement and to use it to prove some vanishing result. So the reason you're going to get a vanishing result is, well, this gives you some information, some bounds on the possible restrictions to inertia of Gauss representations that live inside here. So on the other hand, over here, we have these assumptions here. These are some assumptions on the local Gauss representation. And we're going to see that these kind of assumptions are going to be contradicting information like this, bounds on these inertial weights. These are going to imply that the inertial weights are quite large. These imply that they're quite small. Okay, so that's somehow the strategy. Put those two things together. On the other hand, we certainly can't just immediately apply this theorem off the shelf. For starters, it assumes that the variety already has semi-stable reduction. And that's only going to be true if the level here is prime to p level, effectively. And we want to make a statement about all levels. In particular, we're mostly going to be focused on the Iwahori level. If you, sorry? Yes. Iwahori and pro-p. I mean, let's not distract ourselves too far. But yes, the pro-p or the Iwahori level. And to get the semi-stable reduction there, as we said, as Matt said in his talk, you already have to go up to E being p minus 1. And then information like this is no information at all. So we have to do something a little different. So let me kind of introduce what we would do by maybe seeing, first of all, what kind of information we would get from this in the case of modular curves. So let's think about kind of the very simple case, basically the case n equals 2. So let's take f a weight k modular form. Of level gamma 1 of n. And let's assume for the moment, just so I can be in this world, that p is prime to n. And then we get a Gauss representation, a mod p Gauss representation associated to f, which I'll call rho f bar. And then I could ask when rho f bar could appear in this cohomology where x is going to be the modular curve of level gamma 1 of n. So when can rho f bar appear? Let's ask the question globally in hi x1 of n p dual. So this is now maybe over q bar for the moment. OK, well, for simplicity with these global things, let's just assume that the global representation is irreducible. I certainly don't want to assume the local representation is, but it's going to be simpler to assume this is irreducible. And maybe we won't bother thinking about h2. That's kind of just dual to h0. So let's think about I being 0 and 1. And so for I equals 0, you kind of don't really expect it to show up at all, because you know exactly how h0 is. It's all Eisenstein. And then but even for h1, there's going to be some restriction, because my level is prime to p at the moment, and I've got constant coefficients. OK, so the answer, we kind of know the answer for general reasons, because we completely understand the cohomology of these curves. But let's see what we can say about it just using this purely local stuff. Yes.
When you say it's P, do you mean also inside the etale cohomology, or in terms of like some class with the same vector argument?
It's a good question, and I'm deliberately eluding the difference between these things for a moment. But yes, I mean both those things, and it's going to be the same for this case, but that's going to be an important difference. Yeah. I mean, you might want to just imagine that I mean as a subquotient of the Gauss representation, for example. But yes, the distinction between those two things will become clear in a little bit. OK, so we're making these assumptions. And let's I guess I should have said probably k is at least 2. Well, we have some useful information. We know something about the Gauss representations here. We basically know how they look. We know that rho f bar from this assumption here, restricted to GQP, to IQP, is either going to be of the form an extension of 1 by omega to the k minus 1, or it's actually just going to be 2 powers, omega 2 to the k minus 1 and omega 2 to the p k minus 1. OK? Yes, OK, sorry, let's keep k small. Thank you.
Sorry, that was like a homological normalization, but the top is a cohomology. There's a dual.
There's a dual on the cohomology.
Oh, you took the dual.
Yeah.
Like the glare.
Sorry, yeah. No. I should say that for us, the cyclotomic character is kind of the object with Hodge-take weight 1, and the determinant of a Gauss representation is going to be kind of the positive power of the cyclotomic character rather than the negative power and so on. Yes, sorry, thank you. OK, so in particular, the inertial weights are 0 and k minus 1. OK? Well, then kind of Caruso's theorem is already going to tell us that maybe, in fact, I should just take this up to p so I don't have some stupid issue with omega to the p minus 1. It tells us that we're not going to see anything in H0. So in H0, we're only allowed weights 0. And in H1, we're only allowed kind of weight 0 and 1. And now here we've got 0 and k minus 1. Maybe I'll even go a little further and take this down to p minus 1. Keep making my hypothesis a little more generic. And now so this implies that kind of rho f bar does not appear in H0. And the same thing in H1, unless k is actually 2. OK? And if k is 2, these inertial weights are kind of being forced to be small. They're being 0 and 1. And that's exactly the kind of thing we're going to rule out in our main theorems with assumptions like this. This assumption that your regular of some amount is going to mean that your inertial weights are not too squished together. Like here, the 0 and the 1 are a bit too close together. So of course, this is a bad way to prove this theorem in some sense, because we really, as I say, like the H0 is just completely understood. But when you go up to higher dimensional things, if you even go to a U21, if you're trying to think about the H1 is not something you have such a concrete picture of. And this seems like a much more reasonable strategy at that point. Well, OK, I kind of introduced it by saying that this was all very well, but I was restricted to the kind of good level here, the level not divisible by p. We can see what happens and try and generalize this a bit by going up to some Iwahori level instead. And as you'll see at the end of the talk, as Matt alluded to, somehow if we can prove the vanishing results we want at Iwahori or pro-P-Iwahori level, then we'll actually, by some elementary representation theory, or elementary group theory even, we'll be able to get vanishing at all levels. So this is somehow the crucial case. So in the modular forms world, the crucial case is to think about now kind of f of weight k at least 2 and maybe again I should put it in some small range. Probably I'm safe going up to p minus 1. And it has level gamma 1 of np. And now some p in the level. P doesn't divide n. And I'll give it a Navier-Typist character. Character of z mod p z star. I'm going to kind of implicitly just do p-adic modular forms rather than complex modular forms. And I think I'll probably assume that chi is not 1 as well. Again, some slightly generic assumption that this character is not 1. OK, and now I want to ask myself what I can say about when rho f bar can appear in cohomology at this level instead. So I'll assume that rho f bar is irreducible. It's an assumption. And I'll ask myself, when can rho f bar appear in this hi x1 np? Again, constant coefficients, and I'll dualize. OK. So I can't now immediately apply Caruso's result because I'm asking about, kind of locally, I'm asking about representation of GQP, but this thing is no longer got semi-stable reduction. It's only going to have semi-stable reduction once I go up to QP zeta p. OK? And immediately, if I kind of maybe just kind of go up to QP zeta p, I'm not going to have such good information because for example, I've now killed my mod p cyclotomic character by doing so. So as Matt said, we need to still retain some information. And what we do is we do indeed study the cohomology of this after going up to QP zeta p, so we have some semi-stable model. But we also kind of keep track of the descent data that tells us how to get the Gauss representation back down again. So perhaps I should let M be the corresponding maximal ideal of the Hecker algebra. And then I want to study the localization of this cohomology at the maximal ideal M. And again, this is a slightly subtle point that I will be coming back to, but it's enough checking that this kind of doesn't appear is the same as checking that this localization of this cohomology vanishes. So the kind of equivalent question is when is this localization x1 np bar dual localized at M equal to 0. And again, I'm going to take I as 0 and 1. Well, because I've chosen my Navier-Typist character to be trivial, non-trivial, then in fact this part of the cohomology is living in somewhere with this is only kind of showing up in the parts where there's potentially good reduction, not just potentially semi-stable reduction. So the kind of fact that if I base change to QP zeta p and I can get a semi-stable model, implies the following, that if in one of these degrees the cohomology is non-zero, then there's actually a finite flight group scheme. Finite flight group scheme. Maybe I'll call it G over ZP zeta p. Whose generic fiber is going to be our rho f bar restricted all the way up to GQP zeta p. But this also has descent data given by a pair of characters. And the pair of characters is the trivial character and this neighboring typist character chi bar, which I'm regarding as a Galois character via local class field theory. So this is some other crucial information. This is the descent data is given by this neighboring typist character here. So now, kind of Raynaud kind of classified these finite flat group schemes over rings with small ramification. These finite flat group schemes. And you get rather a short list of possibilities. In particular, if I assume for the moment that I'm in the ordinary case, so I've got niveau 1 characters, there are only a couple of possibilities. So if, for example, rho f bar restricted GQP is reducible, say it's an extension of chi2 by chi1, then it follows from this classification that the restrictions to inertia are contained in the set. I guess you're allowed to have 1 omega chi bar and chi bar omega. Okay, and in fact, if maybe I should use a j there, not to confuse my degree of cohomology, which is I, and if I is 0, in fact, the only possibilities are just 1 and chi bar. OK, so for H1, there's 4 possible characters that could have shown up. H0, there's just these 2. OK, well, we can kind of scratch our heads a little and ask what other information we know. And again, we actually know the reduction of these things very well. And in fact, we know that it's going to be a kind of the trivial here, and chi bar times omega here is actually what shows up in rho f. So in fact, we kind of know for other reasons that rho f bar is isomorphic to, restricted to inertia, gives us chi bar omega star 0, 1. And now you see that we're in some trouble. Again, as long as we're, omega to the k minus 1 here, I guess. I was allowing myself some weight. And again, the list of possibilities is rather small of what can actually be allowed to show up. So for example, if I equals 0, then if we allowed k to be 2, then we've got chi bar omega star 0, 1 is the thing, and this is supposed to be isomorphic to kind of 1 or chi bar star 0, 1 or chi bar. And we're in a lot of trouble unless, unless chi bar is kind of omega inverse. That's kind of the only things that are allowed. So if chi bar is not omega inverse, this is probably a contradiction. So again, we get some good information as long as we're sufficiently generic. We've kind of avoided some small case. We've got that we don't show up in H0. On the other hand, in H1, slightly unsurprisingly, we've shown rather less. That's slightly unsurprising because we know that, after all, the way you construct these Gauss representations is exactly by being inside H1.
Could you say why you are carefully looking at H naught in the global case, of course, H naught will be ruled out because it's a zero type?
Yes, so the point is, just by analogy, I'm trying to go back to a familiar situation. I mean, the case of more interests us is H1 over U21.
Yes.
In that case, I don't, I mean, and if I go back to modular curves, then H0, I mean, the point is, as I'm just showing, the H1 doesn't vanish. So the only thing that kills. So this is a very bad proof. I mean, this is, if I was trying to prove that H0 vanished, this would be a terrible way to do it. But the idea is it's a kind of an analog. So yes, if I equals 1 and k equals 2, then I'm looking at kind of chi bar omega star 0, 1. And of course, both of those characters are on here, and there's no contradiction. And indeed, the Gauss representation will show up. So yes, now let's try and imagine we're trying to prove a non-trivial theorem. We're trying to generalize this. Well, one thing I don't really want to do is to go around making these explicit descriptions like this, okay? Because we don't actually have such nice descriptions of reductions in general. And furthermore, I'm kind of assuming here I came from some characteristic zero modular form. In the kind of theorem I want to do, I just want to have some Gauss representation associated with some maximal ideal, but I don't want to say that this necessarily came from characteristic zero from an ordinary form. That's not the way I want to do things. But in fact, we didn't really need such an explicit description here. We could have got away with something rather weaker. We could have just looked at the determinant. So in fact, we can already get a contradiction. Obtain contradiction from the fact that the determinant of rho f bar restricted to GQP, or restricted to inertia, this is always chi bar omega to the, I guess, to the k minus 1. I was taking k equals 2. So I then took k equals 2 and I equals 0. And I was asking that chi bar omega equals a kind of product of two characters, 1 or chi bar times 1 or chi bar. And again, this has rather few solutions. This imposes very strict conditions on chi bar. Okay? So already, if I made some genericity hypothesis, if I said that chi bar is sufficiently generic, this couldn't have held. And this is the Niveau 1 case, but I could also have done the Niveau 2 case, and I would have been allowed kind of omega 2. Well, in fact, in this case, I would have been allowed essentially nothing, in fact. But in general, I would get some small powers of omega 2. And again, multiply them together, and you're going to get a contradiction. So this implies kind of chi bar cannot be generic. So this is the way we get a handle on things in general, is this rather crude device. Instead of looking at some detailed picture of the representation, we in fact just purely look at the determinant. And already, you know what the determinant should be. And if you've got enough of a bound on the possible characters that can occur in the inertia, if they're all bounded, then their product is somehow bounded, and it just doesn't work out. In some sense, the weights here are, if you think about a chi bar as being kind of some constant small weight, then here you have something of weight 1, and here you just have things of weight 0. The two things of weight 0 can't add up to something of weight 1. So this is exactly the argument we then generalize. So I guess are there any questions at this stage before I?
Can I just
Yes.
ask the same question, or at least remind you to return to the question at some point?
It will absolutely be returned to. Don't worry. So in fact, it's probably going to be returned to in just a moment when I make a list of the things I need to, the ingredients that we've used here. So yeah, so what ingredients did I use in this slightly mysterious proof that there wasn't much going on in H0 of a modular curve? So, well, let me make sure I don't miss any out. So we applied some P-adic Hodge theory. to the FP bar cohomology of a Shimura variety. And if you were here before lunch, then you should be happy that we can do that in some generality. We had some kind of what I'll call a Caruso slash Serre statement on inertial weights. So I'll cover that in a minute. And then we had some argument that we're somehow relating rho f bar and m that I've been skating over, but Frank's been trying to keep me honest, and I will come to that. And finally, there's some argument that we keep alluding to that actually reduces us to the Iwahori level, because our main statement is for arbitrary level, but this kind of all our P-adic Hodge theory is really going on at Iwahori level. That's where our semi-stable models are and so on. So this was Matt's talk, and I'm now going to tell you a little bit about how we've generalized each of these three ingredients. OK. So for the second of these, for the kind of this concrete P-adic Hodge theory, we want a statement like the following, along these lines, that rho bar lives inside the reduction mod P of a potentially semi-stable representation, so PST gamma representation with bounded Hodge-Tate weights and prescribed descent data. We want this to tell us some bounds on the inertial weights. That's what I used. So just some information on the actual mod P gamma representation. So in the argument I just sketched you for modular curves, I really just used some result of Raynaud. More generally, this theorem of Caruso, the kind of hard part is the comparison theorem effectively gives you this information. And then there's some calculation with Broglie modules that's of a relatively formal nature that then gives you these bounds. This is the kind of thing we need to generalize. And luckily, these days, there's a good theory to do this. So there's this theory of Broglie modules. And so Broglie introduced these and made various conjectures about their applicability here. And the theory is in really good shape, thanks to several people. So first of all, Tong Liu proved that given a potentially semi-stable Gauss representation, there is actually a strongly divisible lattice inside this, which is like a kind of characteristic zero version of a Broglie module. So some kind of integral P-adic Hodge theory structure. And crucially, I mean, so Christophe Broglie and then Xavier Caruso had proved the existence of this in various special cases, including when this condition that the ramification degree times the kind of gap in the Hodge-Tate weights was less than p-1. For us, we're always going to have that the ramification degree itself is at least p-1, so we really need Tong Liu's version of this, which has no restriction on ramification. Then Caruso developed a kind of a good theory of how these Broglie modules work in characteristic P. In particular, the kind of thing we're trying to study is we reduce this thing mod P, and I'm really just looking at the inertial weights, which are defined in terms of the kind of inertial characters that live inside this Gauss representation. So this Broglie module corresponds to some n-dimensional Gauss representation. It's really kind of a mess to really, if you wanted to calculate the corresponding Gauss representation, you'd be in a lot of trouble. But what you can try and do instead is think about what possible characters could embed in it, or even just inertial characters. And then you have to know that if you have a character, if you have some sub-Galois character that really corresponds to some sublinear object, linear algebra object. And Caruso developed a nice theory for that. These theories are both without any descent data, though. And as you hopefully saw, if I'd thrown away the descent data in my attempt to prove that H0 was vanishing at Iwahori level, I would have been left with no information at all. So you need a level, some way of incorporating descent data into this. And Dave Savitt did this in the case of p-divisible groups and finite flat group schemes. Well, finite flat group schemes, I guess, is the kind of Broglie-Conrad Diamond-Taylor paper, but the way you actually want to deduce it from characteristic zero, you need to actually have this machinery in characteristic zero as well. And then this was just done for p-divisible groups. I mean, morally, it works in this context as well. And if you kind of take the fiber product of these two things, you get a theory that works in generality, but doesn't really include anything that wasn't proved by these people. And that's in a paper that should be out very soon by the two of us and Florian Herzig as well. So there's a nice theory here. This gives you a kind of theory of all of these things together. Give you a theory of strongly divisible lattices. And Broglie modules with descent data. That's pretty well adapted for making some kinds of computations. I should say, I think I've alluded to this. If I just gave you a characteristic zero Gauss representation, even if it was the Hodge-tape weights were relatively bounded, maybe like just between kind of 0 and p over 2 or something, but there was some ramification, I then asked you to use this theory to reduce it mod p, I think you'd have a very hard time to actually do it explicitly. There are kind of very few cases where anything like this is known. I guess Dave Savitt did this kind of thing for, again, for kind of things coming from p-divisible groups of rank 2 over, which have good reduction over q, p, z to p. And even there, the answer is very tough in general. So you have to work out the reduction of any specific thing. But luckily, the information we need is rather weaker. We just want some very coarse information about what possible characters could embed in there and about determinants and so on. And that's rather easier to treat. So
do you treat any descent data or tame descent data?
This is all just the tame descent data. Yes, you're right. All of these theories are just tame. And in fact, the only one we're using in our talks at the moment is just descent data from q, p, z to p. I mean, I don't think it would be beyond. I don't know there's any kind of fundamental reason why one couldn't hope to get the descent data to work more generally, but I think actually then using it might be. I guess you're one of the few people who has experience of using descent data in non-tame cases. Yes. I suspect that I don't think there's like some intrinsic reason not to be able to do it, but I don't know that anyone has a use for it as yet. And the experience one has of looking at the calculations that result from it kind of is a little off-putting. But yes, the theory for tame descent data is very. I should say that once you have this sufficiently well-developed theory of strongly divisible lattices and so on, that putting the descent data on is essentially a very formal process. That it comes down to essentially one statement about some embedding of some big ring and another one being kind of compatible with a natural Gauss reaction. It's actually very kind of robust in the end. But anyway, I'm kind of getting away from the point, which was I was going to tell you what we proved. So I'll define what it means to be R regular. So I'll say that rho bar from GQP to GLN FP bar is R regular if well, it will have n inertial weights I always have n inertial weights, but I'm going to give them a name. So this is some kind of multiset. They might not be distinct. but I'm going to require they're distinct, and in fact I'm going to require they're distinct even if I translate them a bit. So if the quantities ai plus j with j between 0 and r are all distinct. In kind of, I guess they're defined mod P. So that's some genericity assumption that says I'm not allowed to have kind of, if I want to be 3 regular, I can't have both 1 and omega squared occurring, for example, or even 1 and omega cubed. But as long as things are spaced out nicely, this assumption is satisfied. OK, so that's the definition of R regular, and that's the definition that's occurring over here. And you see that as R gets bigger and bigger, this becomes a stronger and stronger assumption. And then the theorem that just comes from, this is very much like the kind of theorem that Caruso proves, except I'm kind of conflating 2 or 3 results at once here, but this is the kind of result that's well adapted to proving this theorem, is the following. So let's assume that I have a characteristic 0 representation. And this is potentially semi-stable with Hodge-Tate weights contained in the interval from 0 to r. And it has tame inertial type. So it's going to have semi-stable reduction over a tame extension. And this is going to be given by some characters, chi1 up to chi. Sorry, maybe this should be an m. Sorry, I'm going to have an n-dimensional representation in a moment. Let's suppose that there is some number n at most m, which is going to be the dimension we really care about, and integers a1 up to an between 0 and p minus 1, such that if I reduce this tame inertia mod p, I just end up with omega to the power of one of these things, so that each chi I bar is equal to some omega to the aj. So this might well be the same ones. Basically, I really only care about the reduction mod p, and all I'm saying is that when I reduce mod p, the descent data is given by omega to these different powers. Okay. So now I'm going to have an n-dimensional subrepresentation of the reduction mod p of S, and I'm going to draw some conclusion about it. So let's have rho bar from GQP to GLN QP bar, FP bar, which lives inside S bar for some choice of lattice. And let's assume the following things. Let's assume that the determinant of rho bar restricted to inertia is given by omega to the a1, sum of the ai's plus n choose 2. Let's assume that r is at most n minus 1 on 2, and that p is greater than n choose 2 plus 1. So these are some assumptions you can see over there. And assume further that if r equals n minus 1 over 2, then these aren't all, rho bar itself, rho bar semi-simplified is not a sum of characters. So assume it has some bigger than one-dimensional subrepresentation, subquotient. So I'm basically just putting in all the assumptions locally that I made in the main theorem globally. And then the conclusion is that rho bar is not R regular. Okay. So the way we're going to apply this is rho bar is going to be our rho m restricted to GQP. Then we've assumed all these conditions, and we've assumed that rho bar is R regular. And that tells us that we can't actually embed this in the reduction, in certain reductions of potentially semi-stable representations. But the global theory that Matt was explaining last time is exactly telling us, I mean, this S is going to be, in fact, the Gauss representation occurring in the cohomology of some curve that we've got by repeatedly taking hyperplane sections, roughly speaking. And now we're obtaining a contradiction, ultimately. So this is, yes?
Is this just a niveau 1 statement? Your omega, is it?
The descent data is niveau 1. The descent data is always the kind of tame principal series descent data. And the determinant will be, but there's no assumption about the particular characters. And in fact, in the niveau 1 case, if you're in niveau 1, then I'm not actually stating anything if we're in the kind of maximal degree. This statement here exactly says you're not in niveau 1. Okay? Yes?
I'm sorry, Caligari's question again. Rho bar is a sub-thing?
It's coming up in just a moment.
What does the notation mean?
Here's the sub.
Here it's a sub.
It's a
Yes.
sub, yes.
This is just a purely local question.
It's a sub-thing, yes.
Yes.
Okay.
But by choosing different lattices, I mean, I could just say a subquotient. Subquotient would be just as good. Right, so this is our kind of, and this is where all these conditions over here come from. This is just what you can prove using the local information you have at hand. This is how you get a contradiction. Any other questions before I move on and finally answer Frank's question? OK, so Frank's question is where we use this condition here about the image. So roughly speaking, the strategy, the theorem I want to prove is something about when I localize this maximal idea of the Hecker algebra M. And the tools I'm using are about knowing whether the Gauss representation rho m can appear in the cohomology. So we kind of want, let me just be a bit lazy and kind of ignore all the actual coefficients and so on. So we want to prove that HIM equals 0, and we kind of prove that rho m doesn't live inside HIM. This is very roughly speaking what we're proving. But of course, you need to have some connection between these two things. You want to know that when you localize this cohomology at the maximal idea of the Hecker algebra, the kind of Gauss representations that can show up really are these Gauss representations that you've associated. Okay? We need some kind of relationship between these two statements. And, well, what do we know? Well, the Eichler-Shimura relation tells us that if, let me be a little rough, but if L kind of doesn't divide, let's imagine I'm working at some level n, and L doesn't divide NP, then the characteristic polynomial of this rho m of prob L annihilates the action of prob L on this cohomology. Yes. Yeah. Kind of, how should I put this? The characteristic polynomial. I should give this a name. Maybe chi L. Oh, that's a terrible name. OK, maybe I won't give it a name. Kills. If I put prob L into this, I kill maybe the M torsion. So the kind of statement I need if you think about what we want is we want to know a statement of the following kind. If maybe G is a finite group, I mean, I'm talking about representations of G cubed, everything's in characteristic P, so everything's factoring through a finite group. So if G is a finite group, and rho is an n-dimensional representation, perhaps, and maybe theta is an m-dimensional representation. These are irreducible representations. With the property that for all elements of the group, the characteristic polynomial, this is my notation for characteristic polynomial now, of the characteristic polynomial of rho of G kills theta of G, well then I'd like to conclude that these two representations are equivalent. So that would be a good statement to have. So, because then the kind of the study of M and of rho M are going to essentially be the same thing. So that's the situation we need to put ourselves in. If we don't put ourselves in that kind of situation, then we really have no way of comparing these two things, and we don't get off the ground. So this is, it's fairly easy if n equals 1. It's maybe a little exercise. It's not completely trivial, but it's not so hard. And if n equals 2, it's a theorem of Barry-Mazur. It's a very nice trick where you kind of look at the representation and add it to its dual and so on. Many of you have probably seen this. And it's false in general if n is greater than 2, in the sense that you can cook up counterexamples. So for example, if you take G as A4, and rho is the irreducible 3D representation, and then theta is any representation of A4, then the characteristic polynomials of this always kill these things. Okay? And in fact, you have to be a bit careful. I mean, this 3D representation is even induced from V4, so it's not even like there's some, there's some particularly strange example going on here. So, on the other hand, I think it's reasonable to expect that generically this should be true, given enough hypotheses on rho. And we've proved a couple of cases of this. I have to say, if anyone knows any more about this, if anyone knows any general results about this question, I'm sure we'd be glad to hear them, because we certainly don't have definitive statements. But Matt made a statement about an induction, and also we proved this we proved that this is OK if, for example, P is at least n, and this representation satisfies those conditions over there. And I presume that with maybe with slightly different bounds here, you could replace this with other, with like the symplectic group and so on. I think it's a fairly robust argument. But we don't have like definitive conditions for this. So this is where this condition here comes in, or as a version for inductions. So that hopefully answers Frank's question. And if it doesn't, you can keep quiet, because I only have 2 minutes to go. So I should also finally just give you a quick sketch of the main theorem given this. The proof of the main theorem. So let's write the kind of level as k is a part at P and a part away from P. And let's assume this is neat. And let's think of Kp as fixed and Kp varying. And let's write hi Kp for hi of x of Kp Kp Q bar P bar coefficients, and then we want to show, roughly speaking, with all those hypotheses, that hi Kp m is 0 for 0 less than or equal to I less than or equal to n minus 1 on 2. And so the proof is by induction on I. So basically, we're going to apply the Hochschild-Serre spectral sequence a couple of times. Once to kind of make the level very small, and then once to bring it back up to Ihori level. In fact, let me just be quick and just carefully refer to my notes. So if I pass to a normal subgroup of finite index, then I have this usual spectral sequence to compute the cohomology at level Kp in terms of Kp primed. So butting to Hi plus j of Kp. Yes, thank you. Sorry. I think I decided my mind to change from m plus n. OK, so we have this. And if you look at the induction hypothesis, this means that if I prove that these guys vanish, then these guys are going to also vanish. OK? So it suffices to prove that the kind of Hi Kp primed m equals 0. So without loss of generality, from that I can assume that Kp is a normal subgroup of the, this is the pro-P Ihori. So this again is finite index. But now, so let's maybe just phrase this by contradiction, because that's maybe just how I think. So it's assumed that at this level, I have something non-zero. Great, I do have room to write that. And what I want to do is I want to deduce I have something non-zero at this Ihori level. But then again by Hochschild-Serre, this, the level IP cohomology is going to be given by the just these invariants. And now this is a P group. So this would also be non-zero. OK? This is a P group acting on an FP vector space. And so we've reduced to proving that this case, everything vanishes, and that was all the machinery I've been explaining, basically. The argument I gave you for H0 then generalizes with the other observations that we made. So I'm sorry I went a few minutes over. I'll stop there.